Hello, my name is Bas Lodewijks, and welcome to my talk for the German Probability and Statistics Days 2021. In this talk, I'd like to present to you my research on large degrees in weighted recursive graphs with random bounded weights, which is joint work with Marcel Orgis from the University of Bath and Laura Eslava from UNAM in Mexico. The weighted recursive graph model is a generalization of the well-known random recursive tree model, and it allows for much richer and more diverse behavior. So what is this weighted recursive graph model? Well, we start with a sequence of vertex weights wi, which we will take to be i.i.d. random variables here, and we assign every vertex I a vertex weight wi. And then the evolution of the graph depends on these weights as follows. We start with a single vertex 1, and we connect vertex 2 always to vertex 1. And from that point on, new vertices connect to existing vertices with a probability that depends on their vertex weights as such. So vertex weight 3 might connect to vertex 1 with a probability proportional to the weight of vertex 1. Vertex 4 might connect to vertex 1 with this probability. Vertex 5 might connect to vertex 2, this probability, and so on and so on. In general, a new vertex n plus 1 connects to some vertex I with a probability equal to the weight of vertex I divided by the weights of all vertices already present. Now, the picture above here yields a tree, but if we allow every vertex to connect to, say, m predecessors, then we obtain a multigraph. This is the weighted recursive graph model. The behavior of this weighted recursive graph model is highly dependent on the underlying distribution of the vertex weights, and we can classify this into two main classes. And that depends on whether the weights are bounded almost surely or whether the weights are unbounded. You can think of uniform 0-1 weights or exponentially distributed weights, for example, for each of these two classes. In the unbounded weight case, the behavior of the graph is mainly determined by a competition of age versus having large weights. That is, the label of the vertices versus their weights. And this is behavior that is quite different from what is observed in the random recursive tree. When weights are bounded, the behavior is mostly determined by age versus being lucky, where being lucky means that a vertex is able to have its degree significantly outgrow its mean degree. And this is behavior that is very similar to the random recursive tree. In this talk, I would like to focus on the bounded weight case. If you want to know more about the unbounded case, then make sure to check the link in the description to another talk of mine about that topic. So note that if we have bounded weights, then without loss of generality, we can assume that they are bounded from above by 1, because these connection probabilities are invariant under scaling of these random variables. So what we are interested in are degree evolutions. So if we set z and I to be the in-degree of vertex I at step n, when we have a graph of size n, then we are interested in how this vector of in-degrees behaves as n tends to infinity. And in this talk, I want to specifically discuss the maximum degree of the graph. What is its growth rate and what is its location? That is, what is the label of the vertices that attain the maximum degree? Well, let's start by discussing the first order behavior of the maximum degree. Because the in-degree of a vertex I can be written as a sum of indicator random variables, its mean can be expressed as a sum of the connection probabilities. And because of the law of large numbers, when I is sufficiently large, this is roughly equal to m times the weight of vertex I divided by the mean of the weights times log n minus log I. So when I is fixed or not too large, then one can convince themselves that the mean of the in-degree of vertex I divided by log n converges to this quantity m times the weight of vertex I divided by the mean of the weights. Now, as we would expect a vertex with a large degree to have a weight that is equal to 1 or very close to 1, you could think that maybe the maximum degree divided by log n should be roughly m divided by the mean of the weights. So is this true? Well, it turns out that actually the maximum degree is able to grow quicker than this. So if we consider this weighted recursive graph model with bounded vertex weights and an out degree m, if we then set theta m to v1 plus the mean of the weights divided by m, then we find that the maximum degree divided by log n converges almost surely to 1 over log theta n, and this constant is indeed larger than m over the mean of the weights. And very recently, I've been able to show a result on the location of the maximum degree. Under the same assumptions, if we also set in to be the smallest label of a vertex that attains the maximum degree in the graph, then log in over log n converges almost surely to 1 minus theta n minus 1 over theta n log theta n. And this result was previously only known for the random recursive tree, and only convergence in probability had been established. So this is a nice improvement and generalization of that result. Now what we see is that the behavior of the maximum degree in the graph is entirely determined by two things. First of all, the mean of the weights, and second, the out degree of every vertex. The underlying distribution of the weights doesn't really come into play yet. That only happens when we consider the higher order behavior, the maximum degree. And the results that I will present now, we can only obtain for the weighted recursive tree model when m is equal to 1. And we also need an additional technical assumption, which is that the weights are bounded away from 0. This is a technical assumption because we think that this assumption can be either weakened or removed completely with more careful analysis. When we consider the higher order degree, we can distinguish different classes of vertex weight distributions. First, we can distinguish the atom case, in which vertices have a non-zero probability to have a vertex weight that is equal to 1. There is the Weibull case, which is the Weibull maximum domain of attraction, in which the tail of the vertex weight close to 1 behaves like a power law. And there's the Weibull maximum domain of attraction. And here we highlight two specific subcases. The RV subcase, in which the tail of the weights close to 1 behaves like a stretched exponential, and the RAV case, in which the tail of the weights close to 1 behaves like a stretched exponential in the logarithm. So what happens to the maximum degree in this atom class? Well, if we consider the weighted recursive tree model in this atom class, and if we set theta equal to 1 plus the mean of the weights, and we fix some I and j integers, and if we define xkn to be the number of vertices that have degree exactly equal to the floor of log theta n plus k, and x greater equal kn to be the number of vertices with at least that degree, and if we set epsilon n to be the difference of log theta n and the floor of log theta n, then if we take a subsequence nl such that epsilon nl converges to some value epsilon as L tends to infinity, then we can show that jointly this vector of random variables converges in distribution. And these p epsilon I random variables are Poisson random variables. So what we observe here is subsequential convergence, and this is due to the integer valued degrees and this floor that is applied to log theta n, and is what is known as a lattice effect. Also note that this theorem recovers the first order behavior of the maximum degree that we saw before. Now, in this case, the atom class, the weights are able to be exactly equal to 1. In the other classes, such as the Weibull class, this is not the case, and so you would expect the maximum degree to grow slightly slower there, and this is exactly what we see. So if we take, again, the weighted recursive tree model, but now weights in the Weibull class, then we observe the following. We see a deterministic second order scaling of order log n, and it converges to a negative constant minus alpha minus 1. So this indeed shows that the maximum degree grows slightly slower in this case. And we do expect a random third order similar to the atom class, but we haven't been able to prove that in generality. For the Weibull class, we see similar behavior. If we first assume that we have the subcase RV with distributions as such, then we see a second order scaling as follows, where the second order is log theta n to the power 1 minus gamma. And again, we observe a limit that is a negative constant. In this case, the higher order terms are a bit trickier. We expect ceiling of tau many higher order terms, and then an additional random term similar to the atom class. And finally, if we consider the same assumptions, but then the RAV subcase, so weights with such a distribution, then we're able to establish up to fourth order behavior with these constants C1, C2, and C3. And it's not quite clear in this case how many more deterministic scaling random higher order terms there are, and whether such a random order term as in the atom class could be observed. And finally, there's an additional open problem, which is the higher order behavior of the maximum degree location. So as we saw before, we know that the location, when you apply the log and you divide by log n, converges almost surely to a particular constant. But now that we have more precise behavior of the maximum degree in these atom, Weibull, and Gumbel classes, can we say something about, say, the second order behavior of the location of the maximum degree? This is something I've not been able to solve yet, and if you have any ideas or are interested in knowing how this behaves, then make sure to let me know. So thank you very much for your attention, and take care.